In this video we're going to talk about performance evaluation. This will involve applying asset pricing theories such as the CAPM and the multi-factor models that we've looked at to assess performance of a stock, or more commonly a fund or fund manager. So we're going to see how people use asset pricing theories every day in investment management. Before we start evaluating the performance of fund managers, we first need to understand the language. There are two key terms: performance measurement and performance evaluation. Performance measurement involves the calculation of the return realized by an investment manager over some time interval, and this we call the evaluation period. Performance evaluation is actually determining whether the manager added value, so whether the manager outperformed a benchmark, and understanding how the manager achieved the returns they did achieve. So measurement and evaluation are different. We also need to think about how we calculate average returns. You may think this is trivial. Well, let's see. Suppose your investment in year 1 earns returns of 100%, but in year 2 your investment earned returns of minus 50%. The question is, what's your return on the investment? So suppose you make an initial investment of $10, and at the end of each period you rebalance the portfolio to maintain the value of the investment at $10. In year 1 we started with $10, but in year 1 the investment earned returns of 100%. So our $10 went up to $20. What do we do now? Because it says at the end of each period you rebalance to maintain the value of the investment at $10. So we must withdraw $10. Now let's think about year 2. And year 2 we're starting with $10 again, because we've just withdrawn the 10. So we start with $10 and we earn returns of minus 50%. That means we're left with $5. And we've said that at the end of each period you rebalance to maintain the value of your investment at $10. That must mean we have to inject money, and we'll have to inject $5 in order to make our investment value 10. What's the average gain over the 2 years? Our average gain is going to be equal to, in the first year we made $10. We took $10 out because we'd made lots of money. So we've made $10. But the second year we lost 5 because we had to inject $5. So it's 10 plus minus 5. And there were 2 years, so we divide by 2 to calculate the average. That gives me an average gain of $2.5 per year. What's my average return then? Average return is going to be equal to the average gain divided by our initial investment, which was $10. So the average return is 25%. Which sounds quite good. Now suppose we calculate average returns in a different manner. We have the same investments, but now instead of ensuring that at the end of each year the value of the investment was $10, we just adopt a simple buy and hold strategy. What happens now? Well, at the end of year 1, we know our investment is worth $20. But we're buying and holding, so we keep that $20 there in the investment. In year 2, we know the value of our investment falls by 50%. So a half of 20 puts us back down at $10 again. What is our average return? Well, we started with $10 and we finished with $10. So our return is 0%. So we've now calculated average we have now calculated arithmetic average returns and geometric average returns, and look at the differences. Using the arithmetic average, we get returns of 25% a year. Using the geometric average, we get returns of 0% per year. What's going on? Well, the arithmetic mean is typically an unbiased estimate of what you expect to happen in the future. You take the return from each period and divide by the number of periods. For example, in our investments case we've just looked at, in the first period we earned 100%. In the second period we lost 50%. We only had 2 periods, so we divide by 2. And that gives us 50 divided by 2, which equals 25%. The geometric mean is the return that would have been needed to match the actual past performance. And we can calculate the average geometric return using the formula that they've given here. So we're going to do 1 plus the return in year 1, all multiplied by 1 plus the return in year 2, and we're going to keep multiplying by 1 plus the return in each year up until the end of the investment. We're then going to calculate the nth root of that value and subtract 1. It may seem like a complicated formula. Let's actually work through it then. In our example on the previous slide, 1 plus the return in year 1 is going to give us 1 plus 1, which is 2, because the return was 100%, or 1. We have 1 plus r for year 2, which was minus a half, because it was minus 50%. Now let's put these things into the formula. Average return is going to be equal to the nth root. Well, n is equal to 2, so it's the square root. 1 plus r1 is equal to 2 times by 1 plus r2, which is 0.5. And that's all going to be, we're going to subtract 1 from this calculation. What do we get? 1 minus 1, which equals 0. If we're thinking about performance evaluation or performance measurement, if we're wanting to judge how a manager has performed in the past, maybe to reward the manager, the geometric mean may be more appropriate. If we're thinking about what's going to happen in the future to this fund manager and how are they going to perform going forwards, then the arithmetic mean may be a more appropriate measure. But you should be aware of both and that there are big differences between them. Now let's consider how we evaluate performance. There are actually lots of different ways to measure and evaluate the performance of a portfolio or an investment strategy, or indeed an individual stock. There are several important questions we need to consider though. First of all, are we examining well-diversified portfolios or an individual stock? Second, are we comparing the performance of a portfolio to a risk-adjusted benchmark? And third, are we comparing the performance of portfolio A with the performance of portfolio B? For example, we might want to compare the performance of the Henry Fund at the University of Iowa with the Krauss Fund at the University of Iowa to see whether the MBAs running the Henry Fund do better than the undergraduates running the Krauss Fund. The first measure we're going to look at, and one that is commonly used in industry, is called Jensens Alpha. And Jensens Alpha measures abnormal return achieved by a portfolio or a stock relative to a risk-adjusted benchmark. You've actually seen this test before. When we were doing our time series test of the CAP-M and the Fama-French three-factor model, we were effectively calculating Jensens Alpha. Now if you recall, for the CAPM predicts that you're rewarded for taking market risk. So the expected excess returns on a portfolio or a stock is going to be equal to the level of market risk taken on times by the expected market risk premium. And we tested this by running a regression of the excess returns for a particular stock or portfolio. And we tested this by running a regression of the excess returns on a stock or portfolio. And we tested this by running a regression. The dependent variable was the excess returns on a stock or a portfolio, and the dependent variable were the excess returns on the market portfolio. And we wanted to look at the intercept in this regression. If the CAPM holds, then the intercept should be equal to 0. If the intercept, or the alpha, is greater than 0, that's a measure of abnormal return. It can't be explained by the CAPM. So if we see an alpha that is greater than 0 for a particular portfolio manager, it means the manager may have some skill or they may be lucky. But either way, it is an abnormal return. Now the advantages of this measure is that we can evaluate the performance of either a well-diversified portfolio or an individual firm. It can easily be extended to a multi-factor model. So if you wanted to judge performance relative to the 3-factor model or the 4-factor model, you could do it very quickly. You also get some measure of statistical significance. You saw how to construct a t-test to test whether the alpha was significantly different from 0 or not. That way you can ascertain whether a fund manager is earning significant abnormal returns. There is one disadvantage to this measure. You can't use this measure, Jensens Alpha, to compare two well-diversified portfolios. Why not? Well, consider this example. We've got two portfolios, Portfolio A and Portfolio B. The alpha on Portfolio A is equal to 2%, and the market risk is equal to 0.7. For Portfolio B, the alpha is 3%, and the market risk is 1.4. The risk-free rate is set at 5%, and the market risk premium is 5%. Which portfolio is superior? If we just look at Jensens Alpha, Portfolio B must be superior. It's earning an alpha of 3% relative to 2% for Portfolio A. But is it really true? Is Portfolio B superior? We could combine Portfolio A with the riskless asset to form Portfolio C, which has the same systematic risk as Portfolio B. The question is, does Portfolio C have a higher return or a lower return than Portfolio B? How would we do this? How would we combine Portfolio A with the riskless asset to form Portfolio C? Well, we know Portfolio A has a beta equal to 0.7. Portfolio B has a beta equal to 1.4. If we want to get a beta of 1.4 by combining Portfolio A with the riskless asset, what we're going to have to do is borrow money at the risk-free rate and use that money to invest in Portfolio A. So what we want to do is double our investment in Portfolio A and finance that by borrowing at the riskless rate. What happens if we double our investment in Portfolio A? What is 2A? 2A is going to be equal to 2 times by the risk-free rate plus 2 times by the beta for Portfolio A, all times by the expected market risk premium, plus 2 times by the alpha for Portfolio A. Now that's the return on doubling our investment in portfolio A by borrowing money. But we also have to repay the money that we borrowed. And the rate of return, well, we borrowed at the risk-free rate, so we're going to have to repay at the rate of return RF. So what we're interested in is the returns on twice our investment in asset A minus the risk-free rate, because we're repaying, we have to repay what we borrowed. What do we get? We're going to get, rather than 2 times RF, we're doing 2 times RF minus RF. So we're left with RF plus 2 times by beta A times by the expected market risk premium plus 2 times by alpha A. We can substitute in the numbers now, and we're going to get the risk-free rate is equal to 5 plus 2 times beta A is going to be 1.4 times by 5 plus 2 times by the alpha for A, which is equal to 2, which gives us 16%. Portfolio B, on the other hand, only gives us a return of 15%, and yet it's got the same level of market risk. This would suggest that portfolio A is actually superior to portfolio B, and that's not what Jensens Alpha suggested on the previous slide. You could also see this another way. Suppose you're not comfortable with borrowing lots of money and doubling your investment in portfolio A. You could instead turn the problem around and say, I want to invest in a combination of portfolio B and the riskless asset to match portfolio A in terms of its market risk. And we know that portfolio A has market risk of 0.7, while portfolio B has market risk of 1.4. How do we match it? How do we match the market risk of portfolio A? Well, we could invest 50% in T-bills and 50% of our wealth in portfolio B. That's going to give us market risk of 0.7. To see that, let's plug in the numbers. What is our return going to be? Our return is going to be equal to, we invest 50% in the risk-free rate, RF, and we invest 50% in portfolio B, which is equal to the risk-free rate plus the alpha for portfolio B plus the beta for portfolio B times by the expected market risk premium. Close the brackets. If we do this calculation, or simplify this calculation, we get that the return is equal to RF plus a half, all times by the alpha on B plus the beta for portfolio B times by the expected market risk premium. And if we plug in the numbers, that's going to give us 5 plus 1.5 plus 0.7 times by 5, which equals 10. So if we invest in a combination of portfolio B and the riskless asset, such that we have the same market risk as portfolio A, we would earn 10%. But portfolio A earns 10.5%. So we can see again that portfolio A is superior to portfolio B. That's the problem with using Jensens Alpha. Jensens Alpha would have been misleading in this case. Another very common measure is called the Sharpe Ratio. And Sharpe's measure examines fund performance after controlling for the total risk of the fund. What we do is we calculate the excess returns on the portfolio. So we calculate the returns on the portfolio minus the risk-free rate, and we divide it by the total risk of the portfolio, which is the standard deviation of the returns. This is a very easy measure to calculate, and it's useful to compare the performance of two or more well-diversified portfolios. We cannot use it to compare individual stocks or undiversified portfolios, because it's looking at total risk. We also can't calculate statistical significance. What this means is we can't say that portfolio A significantly outperforms portfolio B based on the Sharpe ratio. We don't have any measures for statistical significance. Nevertheless, it's a commonly used measure to gauge performance of a well-diversified fund relative to another well-diversified fund. Trainer also introduced a similar measure, except rather than look at total risk, Trainer just looked at market risk. The advantage again is that this is easy to calculate, and we can compare the performance now of two or more well-diversified portfolios or individual firms, because we're now we're not looking at total risk anymore, we're just looking at market risk. As for the Sharpe ratio though, we still can't calculate statistical significance. We can't say that portfolio A significantly outperforms portfolio B based on the Trainer index. The final ratio that we're going to consider is called the information ratio. This is another very popular ratio. It's used a lot, particularly by Barclays Global Investors, who are one of the biggest fund managers in the world. Formally, the information ratio is calculated as the returns on your portfolio minus the returns on a benchmark portfolio, all divided by sigma epsilon. And you may be thinking, what's sigma epsilon? Sigma epsilon is effectively what we would call tracking error. The portfolio manager may well have been set the target of matching a particular benchmark. So if the portfolio manager outperforms the benchmark, that means his holdings must have deviated from the benchmark. And what we want to capture is how much did the manager's holdings deviate from the benchmark. So you may earn higher returns than the benchmark, but you're penalized for any tracking error relative to the benchmark. And our tracking error is measured using a regression. Our dependent variable is going to be portfolio returns, and they're regressed on the benchmark returns. If you just hold the benchmark portfolio, the error will be 0, because RP and RB are the same. If you've deviated and your holdings are different from the benchmark, then the error term will be non-zero. This is the tracking error. And what the information ratio does is we divide through by the standard deviation of the tracking error. That's the sigma epsilon. The information ratio is decomposing the manager's performance. It's saying, okay, you may have obtained higher returns relative to the benchmark portfolio B, but we're going to penalize you for holding different stocks relative to portfolio B, the benchmark. So we're measuring how much did you deviate from the benchmark in order to gain these extra high returns. If you had to deviate too much from the benchmark portfolio, then maybe that's not a good thing for the fund. We've now looked at 4 ratios that are used frequently in investment management. There are problems with all these ratios. First of all these measures are backward looking. So they may be good for evaluating past performance, but as investors we would also like to estimate future performance. It's not clear that we can predict future performance based on the past performance. If you recall, we saw some comments from a fund manager called Robert Stovall, and he said it's just not true that you can't beat the market. Every year, 1/3 of fund managers do beat the market. The problem is, it's a different group of managers every year. So we really can't measure future performance using these past measures. We can just evaluate what happened in the past. The other problem we have is that our statistical tests for Jensens Alpha may lack power. Often we may only have 5 or 10 years of monthly data for a fund, and yet this may not be sufficient to identify abnormal performance. Suppose a fund manager has a Jensens Alpha of 1% a year. It may not be sufficient if we've only got 5 or 10 years of data. We may not be able to identify this as being statistically significant. He or she may need to keep earning this 1% for 20 years before we could recognize that the abnormal return is statistically significant. That's all I want to cover today. In class, we're going to focus on implementing these tests in Excel. See you in class.